constantly hearing about the future, you know? It's always AI this, crypto that, maybe some space exploration, big topics.
Right, they dominate the conversation.
But today, we're diving into something a bit different. A fascinating set of less discussed technologies that are, well, just as likely to redefine our world in the next decade.
Yeah, think of this as looking under the hood a bit.
Exactly. Consider this your shortcut to getting ahead of the curve on some really interesting stuff.
Our aim here is really to explore these under-the-radar innovations. We want to go beyond just what they are and really get into how they work and, crucially, why they're significant for you, someone who's keen to, get up to speed quickly but thoroughly.
Yeah, and whether you're deeply technical or just sort of curious about what's next, we'll break these down, hopefully spark some aha moments without just drowning you in jargon.
That's the plan.
Okay, let's unpack our first one then. Bioconvergence. What exactly is that?
All right, so bioconvergence is basically this powerful coming together,
Yeah.
a mashup, really, of biology, engineering, computer science, and various other fields. It's about how these different disciplines are starting to feed off each other, enhance each other.
Okay, like different toolkits being used together.
Precisely. And a prime example, especially in healthcare, is the development of organ-on-a-chip technology.
Ah, I think I've heard of this. These are like tiny devices that act like human organs.
Exactly. They mimic the functions of human organs, but at a cellular level. So imagine being able to test new drugs, new therapies on a miniature liver or a tiny heart without needing animal trials.
Wow. So you're basically recreating human biology outside the body.
In a very controlled way, yes.
Right.
For incredibly precise and potentially personalized medical approaches.
That sounds powerful.
And what's compelling here is how quickly this field is moving. The global market for organ-on-a-chip tech is projected to hit around $209 million by 2026.
2026, that's like next year.
Pretty much. And you've already got companies like Emulate Bio, CN Bio. They're actively using these microfluidic systems right now, speeding up drug discovery, refining how we understand diseases. It involves really careful engineering of cell types and how they interact.
So it's not just medicine, though, this bioconvergence idea?
Oh, no, not at all. It's shaking up other industries, too, like food. We're seeing it pop up in the development of alternative proteins. Think lab-grown meat or dairy made through fermentation.
Right, the alt meat burgers and stuff.
Exactly.
Yeah.
And also in creating sustainable biofuels, that alternative protein market alone, forecasts say it could reach something like $209 billion by 2035.
Okay, that's a huge number.
It really is.
Yeah.
So if you step back, bioconvergence is fundamentally about applying engineering thinking to biology and also using biological insights to inspire new engineering.
So teaching biology to do engineering and engineering to work with biology.
That's a great way to put it. And this interaction is driving innovation not just in treating diseases, but also how we produce food, how we generate energy. It shows how we're getting better and better at, well, manipulating life's processes with real precision.
It's definitely a space to watch then, whether you're thinking about, I don't know, future careers or you're just fascinated by this absolute cutting edge.
Absolutely.
Okay, let's shift gears. Second technology. Neuromorphic computing.
Right. Now, think about the human brain for a second. It handles just an immense amount of information, right? Complex tasks.
Yeah, constantly.
But does this using roughly the same amount of energy as a dim light bulb. It's an incredibly efficient biological computer.
Okay, compared to my laptop fan warring away. Yeah, very different.
Exactly. Traditional silicon-based computers are far more energy-intensive for similar kinds of tasks.
And that's where neuromorphic computing comes in. It tries to copy the brain.
In a way, yes. Instead of processing information sequentially through logic gates like normal computers, neuromorphic systems are designed to mimic the brain's structure, its parallel sort of event-driven architecture.
So less like a production line, more like a network.
Kind of.
Yeah.
What's particularly interesting is how it mimics it. By emulating how neurons process and send information through spikes, these electrical pulses these systems can achieve, well, much greater energy efficiency. They can learn in a more biologically plausible way and operate using significantly less power.
Okay, are there examples of this working already?
Oh, yeah. Intel, for instance, they've developed a neuromorphic chip called Low-E-High. It's demonstrated speeds up to 10 times faster than conventional CPUs for certain tasks like pattern recognition.
10 times faster, wow.
And then there's IBM's True North chip. It packs 1 million artificial neurons onto a chip while consuming only about 70 milliwatts of power. Tiny amount of energy.
That's incredible density with minimal power. So what are the big implications then?
Well, it raises some crucial points. We're talking about the potential for robots to navigate complex, real-world environments much more easily, more autonomously.
Huh?
For sensors to interpret huge streams of real-time data using minimal power, think tiny sensors everywhere, and maybe most significantly for AI models to operate without needing these massive energy-guzzling data centers.
Right, the environmental cost of current AI is a big topic.
It is. This represents a shift towards processing information, more like a biological system does. It's not just about faster calculations.
It's a fundamentally different way of computing.
Exactly. Which kind of leads us neatly into our third emerging technology, Spintronics.
Spintronics. Okay, what's that?
So imagine this. Right now, electronics rely on the movement of electrons' electrical charge, right?
Yeah, electrons flowing through wires.
What if, in addition to that charge, we could also harness another property they have, an intrinsic quantum property called spin. Use that to store and process information.
Okay. Harnessing electron spin, how does that help?
Well, our current devices work by moving those charges around. And that movement, it just inevitably generates heat and uses energy. It's like friction.
Yeah, phones get warm, laptops get hot.
Right. But electron spin, it can be manipulated using magnetic fields with significantly less energy loss. Almost none, in theory.
Less energy loss, so more efficient.
Potentially much more efficient. And the market sees this potential Spintronics is projected to reach maybe $25 billion by 2028. A key application here is something called MRAM,
MRAM.
magnetoresistive random access memory, basically using magnetic orientation to store data. And it's shown potential to be, get this, maybe 1,000 times faster than conventional storage like DRAM,
1,000 times.
while consuming considerably less power.
Okay, faster and uses less power. That sounds like a win-win.
Definitely. And the projections suggest that Spintronic devices overall could eventually be maybe 10 times more energy efficient than current electronics, while also offering much faster data processing.
So it's like adding a whole new dimension to electronics.
That's a perfect way to think about it. It opens the door to creating computers and devices that are faster, smaller, and drastically more energy efficient, which is pretty critical as we keep demanding more performance from everything.
Absolutely. Okay, our fourth technology sounds like it goes even deeper. Atronics.
Yeah, this one ventures into an even more fundamental level. Atronics really highlights how science is pushing the absolute boundaries of what we thought was possible.
So what are we talking about here?
Atronics explores manipulating individual atoms, but specifically atoms cooled way, way down to near absolute zero
Okay. Super cold atoms. Why?
to create circuits. Circuits that function kind of like electronic circuits, but they use the quantum properties of these individual atoms instead of relying on the flow of electrons.
Using atoms like transistors. That sounds incredibly precise.
Almost unbelievably precise. It's said that atronomic sensors, for example, could potentially be 1,000 times more sensitive than our current best sensing technologies.
1,000 times more sensitive. How do you even picture that?
Well, think of it like this. If traditional electronics is like managing traffic flow on a big highway,
Uh-huh.
Atronics is like having a private quantum expressway where you can precisely place and control every single vehicle. It's that level of atomic manipulation.
Wow. So the applications, sensors, obviously?
Highly sensitive sensors, yes. And it also holds revolutionary possibilities for quantum computing, which relies on manipulating these delicate quantum states.
Right, taking quantum to another level. Okay, number 5. Let's talk about light. Optical computing.
Yes. Now, we're already very familiar with using light to transmit data, right? Fiber optic cables are the backbone of the internet.
Yeah, light zipping through glass fibers.
But optical computing proposes going a step further, using light itself, photons, to actually do the processing of information instead of using electrons.
So calculating with light instead of electricity, why is that revolutionary?
Well, for some pretty fundamental reasons. First, light travels incredibly fast, significantly faster than electrons moving through a wire. Speed matters.
Okay, faster processing.
Second, photons don't have an electrical charge, so they don't generate heat in the same way moving electrons do. This could lead to much, much more energy-efficient computing, less heat to manage.
Faster and cooler. Are we seeing this happen yet?
We're seeing breakthroughs. Researchers at MIT, for instance, they've developed a light-based chip. It shows the potential to perform certain computations, maybe up to 100 times faster than conventional electronic chips.
100 times faster.
And get this, optical computing could potentially make the training of complex AI models, which is hugely computationally intensive right now, up to 1 million times more efficient, both in energy and time.
1 million times. That's hard to comprehend.
I mean, the potential speed improvements are truly game-changing. Think about it. Tasks that currently take hours, even on supercomputers, potentially done in seconds. In this age of massive data sets, that kind of speed could unlock totally new possibilities.
Absolutely. Okay, let's pivot. Technology number 6 takes us to the ocean. Advanced ocean energy.
Yeah, shifting focus completely. Well, we talk a lot about solar and wind power and renewable energy.
Yeah, they get most of the attention.
The oceans are this vast, largely untapped powerhouse, an immense energy resource just sitting there.
And we're not just talking about, like, old-school tidal dams anymore.
No, not just the big tidal barrages. These emerging technologies are designed to capture energy from a much broader range of ocean phenomena. Things like consistent ocean currents, the temperature differences between surface water and deep water,
Okay.
and even salinity gradients, the difference in saltiness where freshwater rivers meet the saltwater ocean. There's energy in that mixing.
Wow. How much energy are we talking about, potentially?
What's truly remarkable is the sheer scale. The oceans contain enough energy to theoretically power the entire planet many, many times over.
Seriously? That much?
It's immense. And the global market for these ocean energy technologies is projected to grow significantly, maybe reaching $87 billion by 2032.
And I guess one big advantage over solar and wind is predictability.
That's a key point. Many forms of ocean energy currents, thermal gradients, are much more consistent and predictable than waiting for the sun to shine or the wind to blow. Baseload power potential.
But the ocean is harsh, right? Salt water, corrosion.
Absolutely. That's been a major challenge.
Yeah.
But we're seeing advancements in materials, science developing materials that can withstand that harsh marine environment, resist corrosion for long periods, if we can crack that.
We could be on the verge of a major blue energy revolution.
That's the hope, tapping into this huge resource sustainably.
Fascinating. Okay, technology 7 takes us underground. Advanced Geothermal Systems, AGS.
Exactly, down into the Earth's heat. It highlights the just immense potential of the heat trapped right beneath our feet. It's a virtually inexhaustible energy source, really.
We have traditional geothermal, right? Like in Iceland.
Yes, but traditional geothermal has generally relied on finding places where you have naturally occurring hot water or steam reservoirs relatively close to the surface, very location dependent.
Okay, so what makes AGS advanced?
AGS is designed to overcome that geographical limitation. The innovation lies in our ability to create artificial geothermal reservoirs deep underground, essentially anywhere on Earth.
How do you do that? Create a reservoir?
It involves drilling deep wells, maybe several kilometers down, into hot, dry rock. Then, using techniques, some borrowed from oil and gas, like hydraulic fracturing, to create fractures in that rock.
Okay.
Then you inject water down one well, circulates through those hot fractured rocks, gets heated up by the Earth's thermal energy, and then you bring that hot water or steam back up another well to generate electricity.
So you're making the hot spring, basically. Anywhere.
That's the concept, and the potential is enormous. Estimates suggest that widespread adoption of AGS in the U.S. alone could provide enough clean energy by 2050 to power tens of millions of homes.
Wow. Are companies doing this now?
Yes. Companies like Fervo Energy are already pioneering this, drilling these deep geothermal wells, proving the concept can work.
So the promise is clean, constant power.
Clean, constant, baseload energy, available virtually anywhere 24/7, regardless of the weather. It's a really significant step towards a truly sustainable and resilient energy grid.
That sounds incredibly promising. Okay, number 8, 4D printing. Now, 3D printing, most people have heard of that. Layer by layer creation.
Right, additive manufacturing, build something up.
So what's the 4th D?
That fourth dimension is time.
Time. How does that work?
In 4D printing, you use special materials that are engineered to change themselves after they've been printed.
Change how?
They can change their shape, maybe their properties, like stiffness, or even their function. And they do this in response to some kind of external trigger, like a change in temperature or moisture levels, maybe exposure to light.
So the object transforms itself over time.
Exactly. And the market sees this growing, projected to reach maybe $1.5 billion by 2030. Almost like programming physical intelligence directly into the materials themselves.
Programming materials. What kind of applications could that have?
Oh, think about it. Medical implants that could dynamically adjust to conditions inside your body after surgery. Buildings that could potentially self-repair cracks when exposed to moisture. Or maybe textiles, clothing, that could adapt its insulation or breathability based on the environment.
So the applications are really just limited by imagination.
Pretty much. How clever can we be in designing these responsive materials? It opens up a whole new design space.
Okay, that's cool. Number 9, metamaterials. This one sounds like pure science fiction sometimes.
It really does. Metamaterials represent this fascinating intersection of materials, science, physics, engineering.
What are they? Are they new elements?
No, not new elements.
Yeah.
Metamaterials aren't defined by their composition, but by their structure. They are engineered structures, usually designed at the nanoscale, often with intricate repeating patterns.
Okay. Engineered structures. To do what?
To exhibit properties that you just don't find in naturally occurring materials.
Yeah.
They're designed specifically to manipulate waves.
Waves, like sound waves, light waves.
Exactly. Electromagnetic waves like light or radio waves, sound waves, even potentially seismic waves. Manipulate them in ways that were previously thought impossible.
Okay, give me an example. This sounds wild.
Well, researchers at Duke University, for instance, created a metamaterial superlens. It can actually overcome the natural diffraction limit of light,
Which means?
which means it allows for imaging with incredibly high resolution, seeing details smaller than the wavelength of light used, beyond what normal lenses can do.
Seeing smaller than light allows. Okay, that is wild. What else?
And then there's the concept everyone gets excited about, invisibility cloaks.
Right. Can they actually do that?
Well, we're seeing the early stages. Development of metamaterials that can bend specific wavelengths of light, like microwaves or certain colors, around an object in a controlled way, making it appear as if the light passed straight through, so invisible to that specific wavelength.
So not quite Harry Potter yet, but steps towards it.
Exactly. The implications are just staggering, though. Imagine lenses seeing far beyond current microscopes, or materials rendering objects invisible to radar, or perhaps even manipulating sound or heat in new ways. It's a truly transformative field.
Absolutely mind-blowing. Okay, finally, our 10th emerging technology. And you said this might be one of the most foundational, synthetic biology.
Yes, I think it arguably is. And it's important to distinguish this from, say, traditional genetic engineering like GMOs.
Okay, how is it different?
Synthetic biologists aren't just modifying existing genes. They are essentially designing and building entirely new biological parts, devices, and systems. Things that don't necessarily exist in the natural world. It's about creation, engineering life's components.
Designing and building biological parts, like Lego bricks for biology.
That's a pretty good analogy, yeah. And the market reflects this potential, projected to reach maybe $38 billion by 2027. You have companies like Ginkgo Bioworks that at the forefront. They're essentially programming microbes like bacteria or yeast to perform specific tasks.
Programming microbes. To do what?
All sorts of things. Produce sustainable chemicals or fuels, create novel materials, develop new therapeutic molecules, new medicines.
So it's treating biology like a technology, something you can program.
Precisely. Approaching biology, much like we approach computer software, but using cells and biological components, DNA, proteins as the hardware and code.
The applications seem huge then.
Incredibly wide-ranging. Engineering microorganisms to produce sustainable alternatives to petrochemicals. Developing personalized medicines tailored right down to your individual biology. Creating environmental solutions, like microbes designed to efficiently capture carbon dioxide from the atmosphere.
It sounds like it touches almost everything.
It really could.
Right.
It's fundamentally about our growing ability to design and engineer life itself, which, of course, that brings up some pretty profound questions about responsibility, ethics, governance.
Yeah, huge questions there. But maybe for another deep dive.
Definitely. Worth its own discussion.
So, okay. These 10 technologies, bioconvergence, neuromorphic computing, Spintronics, Atronics, optical computing, ocean energy, geothermal, 4D printing, metamaterials, and synthetic biology, they really give us a snapshot, right? A glimpse into some of the most exciting and potentially world-changing innovations bubbling up for the next decade.
It's just a snapshot, yes, but a potent one. And what's particularly fascinating, I think, is to consider how these technologies won't exist in isolation, how they might converge and sort of amplify each other's impact.
Right, how they might work together.
Exactly. Imagine bioconvergence research being supercharged by the energy efficiency and processing power of neuromorphic computing, or complex metamaterials being fabricated with the adaptive precision of 4D printing.
Or maybe synthetic biology breakthroughs being accelerated by the sheer speed of optical computing for simulations.
Precisely. The potential for these synergistic interactions, these combinations, is immense. That's where things could get really interesting really fast.
And I think maybe the most important point to take away from all this is, well, the future isn't just something that happens to us, is it?
No, absolutely not.
It's being actively shaped right now by the choices we make, the research we fund, the investments we prioritize, the innovations people are pursuing in labs and startups around the world.
It's being built, decision by decision.
So as we've explored these emerging technologies, it feels crucial to think not just about, wow, what becomes possible, but also what kind of future do we actually want to create with these incredibly powerful new tools?
That's the key question. It moves beyond the purely technical.
Yeah, it's about the human element.
So maybe a final thought for you to consider as you mull over these 10 areas.
Yeah.
What do you see as the most pressing challenges facing humanity right now? And looking at these technologies, could one, or maybe a combination of them, offer a pathway towards a solution that resonates with your vision for a better future? Something to think about.